Howdy. The purpose of this video is to review the filling rules for electronic orbitals. So why do we care about how electronic orbitals are filled? Remember, solids are aggregates of many, many atoms that have come together and are bound together by some sort of chemical bond. And the nature of those bonds that are holding the atoms together is related to which electronic orbitals are filled and which orbitals are unoccupied or partially occupied in different neighboring atoms. So in order to describe and understand how solid matter is held together, we need to know something about the various energy levels of the electrons in different atoms. Okay, so what am I showing? Off to the left, we have a plot of energy versus nothing. I've sort of arbitrarily spread them out on the x-axis here. But this is describing the energy level of different electronic orbitals. So for an example, the 1s orbital, this is, again, remember 1s is given by the principal quantum number equaling 1 and the angular momentum quantum number equaling 0. So these are spherically symmetrical orbitals. So the 1s orbital, we see it has a very, very low energy state. Now, the convention is for lower energies to be more stable. So you can think of these as very tightly bound electrons. You can think of them as being in the most stable state. And that makes sense because this is the orbital that is closest into that nucleus. It would take the most energy to remove an electron from that orbital. So these are the most tightly bound electrons. If we look at the next shell up, so n equals 2, again, this is the principal quantum number. For n equals 2, I can have s orbitals and I can have p orbitals. Now, as before, s orbitals can only take 2 electrons. So I have one box here that can hold 2 electrons. The p orbitals, on the other hand, can hold a total of 6 electrons. And that's because, remember, there's 3 different orientations of the p orbitals. These are sometimes called px along the x-axis, py along the y-axis, and pz. And each of those orbitals can hold 2 electrons. So I've illustrated 3 boxes here. Each of those is able to accept 2 different electrons. So what do I see about the relative energy of the n equals 1 electrons and n equals 2 electrons? Well, immediately I can tell the n equals 2 electrons are a much higher energy level state than the n equals 1 electrons. So these are a little bit less tightly bound. The atom is holding on to them a little bit weaker. It's easier to remove an electron from these orbitals than it is from the 1s orbital. We also see that within the second shell, so within the n equals 2 quantum number, the s electrons are more tightly bound than the p electrons. So this is also going to be the case as we go out to larger and larger shells. So for n equals 3, the third shell, s has a lower energy level than p electrons, which are also lower energy level than d electrons. Now, as before, d electrons, now there are 5 different potential orientations, so I can take a total of 10 electrons. Okay, one thing we do start to notice is that as we go out to higher and higher principal shells, so larger principal quantum numbers, we start to see an overlap. So there's an overlap between the energy levels of these 3s, 3p, 3d, so the third shell electrons, and energy levels of the fourth shell electrons. So what does this mean in terms of filling? So let's come over to our periodic table here first. So if I'm going to start with atomic number 1 and move up in the periodic table, for each sequential atom, I'm always going to fill the lowest energy levels first. So for hydrogen and helium, hydrogen has 1 proton, helium has 2 protons. So a neutral hydrogen will have 1 electron, and neutral helium will have 2 electrons. And so these are going to go to the lowest potential energy orbital that they can sit in. That is, the ground state is for these electrons not to be excited and for them to sit in the lowest potential energy position. This is the hydrogen and helium fill up our 1s orbital. As we go to the second row, first we're going to fill up the 2s electrons. That's filled by lithium and beryllium. And then we're going to start to fill up these 2p electrons. And that's because, again, the 2p orbital is at a little bit higher energy level than the 2s orbital. And so there are 3 potential orbitals. Each of those can have 2 electrons, spin up and spin down. And so that gives us 6 electrons that we're able to put into the 2p orbitals. Okay, moving on, we're going to then fill up the 3s orbitals. Again, I can put 2 electrons in there. And then the 3p orbitals. Again, a total of 6 electrons would go in there. So what comes next? And this is a case where, again, this overlap between the 3rd shell orbitals and the 4th shell orbitals comes into play. So if I'm strictly filling them up from the bottom up, the 4s electrons, the 4s orbital rather, would fill up first. After I filled the 4s orbital, the 3d orbital is going to start to fill up. And so I can take a total of 10 electrons here. And that is why the transition metal block is 10 columns across. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, but things get a little complicated towards the middle, and that's just because these d and s orbital energies are very close to each other. So this manifests itself in a couple ways. First of all, if I get to something like copper, for example, if I was going to fill them up as is shown on this diagram, I would put in 2 4s orbitals and then 9 3d orbitals and call that good. Well, a full orbital has a lower overall energy than a partially full orbital. And it turns out that it's energetically favorable to bump up one of these 4s electrons so that copper has a full d orbital set. So the structure of copper, we could say it's given by argon 4s1 3d10. So this notation means that I'm starting with the stable argon electronic structure, and then on top of that I have 1 4s electron and 10 3d electrons. So rather than being 4s2 3d9, it's a more stable, more favorable configuration for that d orbital to be totally full. The other way this manifests itself is when I'm looking at cations in the transition metals. Oftentimes I will lose s electrons before I lose the d electrons. So for example, iron 2 plus, so pure iron would be given by argon 4s2 3d6, but iron 2 plus is given by 3d6. So I actually am going to lose the s electrons first. And all of this is just because the d and the s electrons are very close in terms of their overall energy level. And it gets particularly complicated as we go out to larger and larger energy levels. Okay, so what else? What are other important things? The bonding in solids is going to be a function of those electrons at the highest energy level. So those that are least tightly bound, those that are most able to interact and be affected by the surrounding atoms. Because what is a bond? It's some sort of interaction between the electron density of one atom and a neighboring atom, right? So we break up all of the electrons in the filled orbitals into what are called core electrons and valence electrons. So core electrons are those that are very tightly bound and they don't really participate in any sort of chemical bonding. Valence electrons, on the other hand, are less tightly bound. They're more likely to be stripped off. They're more likely to be shared with other neighboring atoms. So as an example, the valence electrons are always those electrons at the outermost energy level. So if I was looking at something like a row 2 atom, lithium has a partially filled 2s orbital. So in this case, I would call the 2s electrons would be valence electrons, but the 1s electrons would be the core electrons. If I go to something over here, like carbon, now I have 2s and 2p electrons. And in reality, the energy levels of these two are close enough that they're both affected by surrounding atoms. And so in carbon, the valence electrons are the 2s and 2p electrons. And in fact, oftentimes in carbon, these will combine together to form what are called hybrid orbitals, so sp orbitals. And again, the core electrons are the 1s, those interior strongly bound electrons. Same thing in transition metals. So for example, iron, the valence electrons are given by these 4s and 3d electrons because they are the electrons that are closest to that. They're the least strongly bound electrons. They're the highest energy level electrons, and they're most likely to be stripped off and to interact with surrounding atoms. Okay, so how do we know this? Let's come to a very specific case. This is what is called an electronic spectrum for gold. So there's a technique that we use to measure the energy levels of different atomic orbitals. And this is called X-ray photoelectron spectroscopy. The thing that I want you to know about this technique is that it's very surface sensitive, but you are able to probe the structure of an atom and you're able to get the binding energy of different electrons out. So if we look at binding energy, that is how strongly are these electrons bound to an atom. So we're going to start at the highest binding energy, and we're only able to see kind of the outermost electrons in this case. The other electrons still exist in the gold case, but they're very, very tightly bound, and we're not able to probe those with this technique. So the first orbital we see is the 3d orbital, and that has a binding energy of somewhere around 2200 electron volts. And these are very strongly bound electrons. They're not going to interact with neighboring electrons at all. So somewhere up here at a much lower energy, we see the 4s electrons. So this picture that I described before, this is a case where, again, as I fill up an atom, the relative energy levels of these different orbitals is able to shift around a little bit. So in the gold case, 4s is above 3d, so it's at a higher energy level. We also see 4p and 4d, 4p, 4d, and 4f is just above 5s. So again, 5s would be just below 4f, and then 5p and 5d higher up here. If I look very, very close to, if I look at very, very small binding energies, these are energies that are very, very weakly bound electrons. I see a combination of 5d and 6s electrons. So in gold, this is what I call the valence band. These are the least tightly bound electrons, and it's composed of a combination of 5d and 6s electrons. If we jump back to our periodic table, this makes sense because we have the 5d electrons and 6s electrons, and these are the highest energy level electrons.